and seeing the screen. So first of all, sorry for these technical issues that forced us to start a little bit late. So welcome to the training action on B-WaterSmart tool 24 regarding the water quality modeling in inland water distribution systems. I am Maria João Rosa and a researcher at ELNEC, the National Civil Engineering Laboratory, and I'm the mentor of the Lisbon Living Lab within B-WaterSmart. That is why I am most pleased to welcome you to this training action on in my name and also on behalf of ELNEC, of the Lisbon municipality, here by Pedro Teixeira and by base forum Sérgio Teixeira Coelho, who are both here with us. So today we will be having two consecutive sessions. First, this online webinar, and then a training action hands-on on the software. Our agenda will be, first we will start by an introduction to water quality modeling in distribution systems by our colleague at ELNEC, Rui Viegas, and then the B-WaterSmart tool will be presented by Baseform, by Sergio, and also by Rui in all these topics. So introduction to the tool's objectives, inputs and outcomes, introduction to the operating environment and overview of the user interface, how to configure the input files, how to run the analysis, how to examine the results in the software, and how to export the results to common formats to be able, as the users want it. We will be having the discussion, the Q&A period at the end of the webinar, prior to its conclusion, planned for 1.5 hours from now. So moving now to so this is the fourth training action of the Lisbon Living Lab tools. We have already the climate readiness certificate, and then the urban water cycle observatory. Yesterday we had the seminar for the 3 of the 4 tools that constitute this tool set on smart water allocation, and the last one, which is regarding the treatment technology that we are also developing and testing, will be next month, so April. About today's software. As I was introducing, our objective is framed by the strategic objectives that we have set for the Lisbon Living Lab within B-WaterSmart. We want to reduce on the short term the freshwater dependency for non-potable uses, and we want to introduce standards for buildings. And regarding the promotion of non-potable water reuse, to facilitate such promotion, we developed a set of 4 digital tools. The 3 of them, or at least 2 of them, mostly connected with the planning of the solution, meaning the water-energy-phosphorous balance planning, yesterday introduced as the matchmaking, which balances the demands and the supplies, available. And then 2 tools regarding the risk management when we are using the alternative supply of reclaimed water for its very resilient characteristics, since it is the most rainfall independent source. yesterday again we had the risk assessment tool for urban non-potable uses, and today we will be having the water quality model, and all of them will be are to be ultimately integrated in a decision support and selection of alternative courses of action, which is the tool 17. And what's the point of having this water quality model? The point is that we need to ensure that the quality of the water, that the reclaimed water, is not degraded from the point of production until the point of use. And we all experience, those who are working on water reuse all experience in hot climates when the water reuse is more needed, often the water quality, there's a bacterial regrowth within the distribution system, so we need to control it, so to manage the risk of reclaimed water use. And having said that, all these technologies are tested in or were tested within several pilots, and we will be also seeing this today in Rui's presentation. And having said that, I think we can now give the floor to Rui, the developer of the water quality model, and then how he will explain us, and Serge will explain us how this turns into a digital tool. So enjoy.
Good morning, thank you. Good morning. I will be before we start the demo, we show you the demo of the tool, the live demo. I will do a brief, or not so brief, maybe introduction to water quality modeling in distribution systems, showing what these models are, how to set them out, and focusing also, or mostly, our work performed in the B-WaterSmart project. So, starting with a brief historical introduction, these computational models that simulate water quality in distribution networks emerged in the 80s, following the widespread use of hydraulic simulation. They start with a network hydraulic solution with a complete description of flow rates and speeds, and they calculate the movements along the sections and the mixing in the nodes, mixing of those substances present in the water or other characteristic parameters, for example, residual chlorine. For non-conservative substances, they also simulate their transformation, which can be a decay or a growth over time with this movement of the water. So they calculate the travel time, and in summary, they start with a flow rate, with a velocity, with a concentration at time 0, and they calculate for along the time the concentration of that species. So they have been applied, or they can be applied to simulation, describing the processes that occur in the systems, but they also can be used for process optimization, for searching for an ideal solution to a design or operation problem. So examples of uses that can be used for optimization of disinfection processes, if you know the disinfectant concentration, for example, that you need in a distribution system, you can optimize the disinfection process uphill. For predicting the potential quality degradation issues, as Maria João already spoke about. For minimizing travel times, time is very important in the distribution networks. For predicting the effects of reservoir storage, for planning monitoring or sampling programs, online monitoring or sampling programs, to control the water mixing in systems with different water sources, which is an application very used in this type of problems. For comparing operational strategies, the way that we can operate the distribution systems, for example, So in conclusion, water quality models should play a central role in the planning, both in the planning phase, in design phase, and also in the operational control of the distribution systems. So what's water quality parameter to monitor is to guarantee a safe application at the point of use. For sure, the disinfectant concentration, which is the key barrier for water microbial stability. And the most used disinfectants worldwide is the residual chlorine, which can be monitored online and can be used for compliance with legal limits from microbiological quality, as it minimizes biofilm development, it provides protection against contamination in distribution network, and it also constitutes a contamination alert parameter. If, for example, if there is a sudden decay of chlorine of disinfectant in the distribution system that is alerted, it is possible to know that contamination occurs in the distribution networks, for example. We can also also monitor microbial contamination, but it's an offline parameter, usually an offline parameter that is monitored. We can think also of measuring turbidity, which can be measured online, but it's typically more expensive to do it. And we have advanced monitoring possibilities like fluorescence spectroscopy or UV visible light absorbance, which can be performed online for other characterization, for example, of organic matter. So how do we typically develop a chlorine decay model? We must start with an hydraulic model, a well-established hydraulic model, which considers both transport and mixing. And we must build a kinetic model considering the decay of chlorine in the water, considering the reactions of chlorine with water species, in particularly reduction species that can be reduced, typically metals, or in considering the case of reclaimed water, ammonia is very important for this case. Yeah, and also the organic matter, of course, and this ideally independent or considering the changes in chlorine dose, concentrations of these inorganic and organic compounds, and the temperature. But we also must consider the kinetic decay of chlorine regarding the reactions of chlorine with the pipes, both with material of the pipes and the biofilm that might develop in those pipes, and also reactions with sediments. These reactions depend, of course, on the pipe material, on the network conditions. If it is if it has biofilm growing in it, it will increase this decay of chlorine in the water, and so of course also on the flow conditions. So our aim is to develop predictive modeling that can cope with changes in applied dosage of chlorine, and also can cope with rechlorination that might be needed in the distribution system, and also that can accommodate changes in water quality, for example, pH, temperature, organic matter, all this in transient states and with accuracy. That is our aim, and should be the aim of people that want to develop a sound model in distribution systems. So regarding the methodology to develop this kind of models, we should carry out work in the lab and at full scale in the network. We start with a hydraulic model, with building and calibrating an hydraulic model based on data, registry data, including data of the elements of the network, like the diameters, the length, of the links, for example. We must know the operational the operation data of the network, how it is operated. We must have the water consumption data for the network, and if needed, we should calibrate it, the network, the hydraulic model with flow rate measurements campaigns. So then in the lab we perform chlorine bulk decay kinetic experiments for building this quality model that is embedded then in the full scale model. So we do then with the full scale model we perform the simulations with the lab constants regarding this chlorine bulk decay, and so we do full scale flow rate and water quality campaigns. Then we check if the results of the modeled chlorine decay is and the measured and the modeled coincide, and and we do it this process iteratively until, and we adjust this decay, the wall decay, until the results of the model and the measured chlorine in the network are the same. So then we have the water quality model validated. So just a brief explanation on the chlorine bulk decay kinetic experiments that are typically performed. So we do the so-called bottle tests, which consist of dosing chlorine with several initial concentrations to the water that we want to characterize, and sample it at several time intervals, typically using the colorimetric DPD method to quantify the chlorine, the several possible species of chlorine. And then we model it, we implement the model, and typically we have a profile of chlorine decay as is shown here. We have a steep decrease in the beginning of the dosing. After the dosing, it is called typically the instant chlorine demand, and then we have a slower phase of decay of chlorine. The reaction is something like this. Chlorine reacts with some reagents and produces products. And what the models that are typically used are which are already implemented, for example, in EPANET modeling software. First order models that we can see here that cannot capture this fast and slow decay of chlorine. Also can be used in EPANET. This limited first order model can also be used, which is represented here by this green curve here, which doesn't capture also this two phases decay, or this n order decay of chlorine, which provides more accuracy to the data. Regarding drinking water, there is a model that was developed in the late 90s, last century, by Clark, which is a parallel second order, which is a model that fully captures and has some mechanistic behind it, captures this two phases decay, and this is very popular for modeling chlorine decay in drinking water. Well, in drinking water, going a bit on the chemistry of the thing. In drinking water, the reactions involved are quite simple. We have the equilibrium between the free chlorine species, the hypochlorous acid and the hypochlorites. We have this stage. This is the residual chlorine concentration as a function of the residual of the chlorine dosed. We have this stage when there is no residual chlorine. It's the fast decay zone. Then we have the free chlorine, the residual free chlorine in the water. When in reclaimed water, we have an additional problem because we have typically ammonia, and we see that all those reactions that are depicted here in this table occur. This is a set of 14 reactions that unfold when dosing chlorine to a water that contains ammonia. And the first reaction, the reaction that starts is all of these set of reactions is the reaction of hypochlorous acid with ammonia, producing monochloramine. Monochloramine is a disinfectant. Disinfectant is also a disinfectant, not as free chlorine. It doesn't have the same disinfecting power. Well, it's different. It's also a disinfectant, of course, but it does not possess the same disinfecting power. But on the other side, it has a slower decay, so it has advantages and disadvantages. I will show you a bit about this later on. So it is when we dose, as we can see here on the left, when we dose the free chlorine to a water containing ammonia, we have this first phase where monochloramine is formed. After a dosing concentration of about 5 times the free chlorine to ammonia, we start destructing this monochloramine, forming dichloramine, and only after about a weight ratio of chlorine to ammonia, about 7.5, we'll start having free chlorine. This is a theoretical ratio, but in practice it occurs typically on about 12 or even more, a ratio of 12 or even more of chlorine to ammonia. So if we have, for example, a water with a ammonia concentration of 1 milligram per liter, for example, only by dosing a concentration of chlorine about 12 milligrams per liter, we'll start having free chlorine. Before that, we'll have monochloramine. So, and these reactions are regarding the inorganic matrix of the water. And we also must consider, of course, the reactions of chlorine with the organic matter present in the water, and which, given the fact that we have several chlorinated species here, like free chlorine, monochloramine, dichloramine, we developed a model and published the results of this model, identifying the species that react with this fraction of the organic matter that reacts fast and or slowly with chlorine. So just to summarize what I've been saying about the different type of models, we have this mechanistic model that has four parameters, which are the parameters. Let me just go back a bit. The parameters of these reactions, the concentration of this fraction of organic matter that reacts fastly, and the concentration of the organic matter that reacts slowly with chlorine. And we have these two kinetic constants. This is a model that is, I would say, it's very complex to calibrate. Its implementation is complex. It's not possible to do it in EPANET, but it can be done, for example, in a freeware EPANET MSX and in base form platform, of course. Well, it has an excellent accuracy both for drinking water and for reclaimed waters, and it has a predictive ability. It can predict the chlorine in the water and other water quality parameters like pH, alkalinity, ammonia, organic matter, and we have this second model that I talked about before. I cannot show that. This parallel second order developed by Clark, which is semi-mechanistic. It's also complex to calibrate, not so complex as the previous one because of the number of reactions involved. It's not that also that easy to implement. Cannot be done in EPANET, for example. It has a very good record for a very good accuracy for drinking water, and not so good, but good for reclaimed water. It has some predictive ability, can predict chlorine if you know in which zone of the disinfection you are, if you have monochloramine or free chlorine, but it has no prediction ability for the other water quality parameters. And the other parameters are more, the other models are more simple. What? Sorry about that. And we have these three other models that I've talked about, which are more simple, of course. These two have only 2 parameters, and the first order is 1 parameter, but they have no prediction ability towards the nor chlorine nor the other water quality parameters. Though more simple and easily implemented in the EPANET, but no much use for it. So regarding this advanced mechanistic chlorine residual modeling that I've been showing, they have the prediction, they have predictive ability and allow to control the reclaimed water quality at the point of use. This is at its use after the distribution network. They allow to predict the chlorine dosing requirements at wastewater treatment plants outlets, because if we know the chlorine in the point of use, we can design the chlorine dosing for the wastewater treatment plants. They can help in the operation and design of the distribution system as to guarantee a disinfection of the treated wastewater, and of course of the distribution system, and also for minimizing disinfection byproducts formation. We can also put in this model, for example, the trialomethane formation potential, knowing the concentration of chlorine, or knowing with accuracy the concentration of chlorine. And this can also this type of models can also be integrated in the tools that Rita showed yesterday, the risk assessments and the smart allocation tool, for example, as they can be used for risk assessment and risk management. I don't know if there are some questions regarding this part of the presentation. Because then I will switch to the work that we have been carrying out in B-WaterSmart, if someone has some questions. I tried to be as simple as I could, but this is okay. So I'll proceed with the work we carried out in B-WaterSmart. So in B-WaterSmart,
and whenever some question arises, you can write it down on the chat, so we can then
of course,
try to address it.
Yeah.
Thank you.
So in B-WaterSmart, we had three pilots served by 2 wastewater treatment plants. From Alcântara wastewater treatment plants, we had 1 pilot for green roof irrigation, which is in use. We have also a second pilot from network from this wastewater treatment plants which is intended for green spaces irrigation and for street washing, that a pilot network pilot that goes to the riverfront of Lisbon, which uses on approval, and is also being used now for washing of equipment of the wastewater utility in lifting stations. We have a third pilot from Bairrolas wastewater treatment plant or water resource recovery facility that serves for garden irrigation in the Parque das Nações Norte, which is the north area of Lisbon that is in use since July 22 in the middle of our experiments. So we applied the methodology that I've explained before. We have developed the chlorine decay within the water model that I've shown before. We did the hydraulic modeling of these distribution networks, and we implemented this full water quality model in the distribution networks. Just a quick overview of the work we have developed. So for pilots 1 and 2, we see here the images. We did campaigns. These are representations of the full-scale campaigns that we did. We did monitoring of quantity of quality during 3 days. The parameters are here depicted. I won't go into much detail on it. Just to say that the water, the reclaimed water that was produced in this water reclaim facility has a high content of ammonia. For example, it has 14 milligrams per liter of nitrogen. It was not fully disinfected before dosing the chlorine, of course. We had a dosing of chlorine about 4.6 milligrams per liter. No E. coli detected after disinfection, and in the irrigation distribution system we had a high level of chlorine because it was very near to the dosing point of chlorine. No E. coli, and at the end of this distribution network, we had a low concentration of chlorine, but yeah, particularly and also disinfected. With the results of these campaigns, we published a scientific paper. So regarding this pilot 3 in the Parque das Nações Norte, it's a very long network, a very intricate network with 8 kilometers long, and about almost 3,000 irrigation points divided in 246 irrigation sectors. I show here an image of the calibration of the bulk decay, bulk chlorine decay. We also had a very high concentration of ammonia at this stage of the project, about 23 milligrams per liter of nitrogen. We dosed it, for example, between 8 milligrams per liter and 50 milligrams per liter of chlorine, and we see that the model follows the chlorine residual concentration quite nicely. I have here a video that we did by simulating this distribution network with a chlorine dosing of 5.5 milligrams per liter. I will show it just to. This was implemented in Baseform software. You can now have a look of how it runs. It was in the earlier phase of the development of this platform. Still starting to dose the chlorine, and we see that, for example, that we might have some spots that don't have the chlorine that was needed. Some spots that could be critical, that should be carefully looked at. Especially this endpoint here. So the platform allow us to implement this complex model and to look at the network in its full extent and understand critical points of the network, points that and show us if we need to dose more chlorine or look particularly at those points. This was this pilot 3, and it was in the earlier stage of development of the tool. So then we had a last pilot, a more simple pilot than this third pilot, which it is a distribution network that was built for the World Youth Day that took place last August in Lisbon. This was a newly constructed network to irrigate this park that was built for the World Youth Day. It is a 38 square hectometers park with a almost 60 kilometers long network with 108 irrigation points. The hydraulic, the rotation time in the tank that was serving this distribution network is about 24 hours. And this was the water quality that reclaimed water has, about pH of 7.8, TOC content of 4.4 milligrams of carbon per liter, alkalinity of 210 milligrams per liter, and these are the inputs of the model. We simulated this for 2 ammonia concentrations, one with virtually no ammonia, considering 0.025 milligrams per liter of ammonia, of nitrogen, and another one with 2.5 milligrams of nitrogen, and we simulate a chlorine dosing of 2 milligrams per liter. Regarding the operation of the network, it is being the irrigation is taking place between midnight and 7 a.m. with 1,600 cubic meters per day, constant along the week. And I have here some graphs of the concentrations of chlorine and monochloramine depending on the situation. And for the source, for the tank, and also for 2 nodes, one that irrigates in the beginning of the operation, and another one which is far away from the tank. On the left we have the situation with of the water with 0.025 milligrams per liter of nitrogen, and we have here the source water concentration of chlorine, and we can see that we are dosing constantly at 2 milligrams per liter. We have about after this is the startup of the network, and at steady state we see that we have in the tank concentration about between 0.5 and 1.1 maybe of free chlorine. And if we look at this and at these 2 nodes that I referred, the node more close to the tank and which is farther than to the tank, we have concentrations between little less than 0.5, maybe 0.4, and 1 milligram per liter of free chlorine in this situation. If we have 2.5 milligrams of ammonia, we then don't have any free chlorine, and we have monochloramine as the disinfectant, and we can see here the profile in the tank, the monochloramine profile in the tank. It's about between 1 and 1.5, and in the nodes we have between 1 and 1.25 in these 2 nodes that I've mentioned previously. We can see that we have a lower concentration of the chlorinated species here, which is free chlorine in this situation, between 0.5 and 1. Regarding if we have ammonia in the water, we have a higher concentration of chlorine, of total chlorine, in fact, but between 1 and 1.25. So, but what is important to mention, as I said before, the free chlorine has a higher disinfectant power than monochloramine, and this is a good situation. The good range of chlorine in a distribution network should be between 0.5 and 1.5. It can go up to 3 milligrams per liter, which is no problem. So in this situation, we have concentrations that are okay for managing this network and for having a disinfected network. But in this situation that we have ammonia and we have the formation of monochloramine, as we have a concentration between 1 and 1.25, we will be always in this alert phase. So it's not, it shows the importance of knowing which disinfectant and in which side of the disinfection process we are. So I'll show here the full depiction of the network for both situations. When we have the free chlorine formation with the low contents nitrogen water and the monochloramine monitoring, and we see here that we are almost always in the alert phase, while here in this situation we are mostly in the good operation of the network. These are prints from the base form software that will show afterwards. I don't know if it was clear, if there are some questions regarding this stage of the presentation. Otherwise, I'll give the floor to Aisha, I think, to Sergio.
That's it. Let's just mute our computers. We're sitting next to each other. Okay, it works perfect. Can you guys hear me? Okay. Good morning, everybody. Thank you for joining this session. Thanks, Hui, for this very detailed explanation. I'll give you very brief introduction to what has been done in the software, and then I'll pass this to what really matters, which is for you guys to see the software, and Aisha will take it from then on. So let me try to share my screen. You should be seeing a slide with a green chart. I assume you are seeing that slide. So this is just basically to give you some background on how this has been implemented in the project. As you may know, if you were here during in yesterday's session, or if you've been following the project, this is the tool we're talking about today. Is one from a set of 4 tools that were developed, that were conceived by the Lisbon team, particularly LNEC, and implemented by ourselves, Baseform. The schematic on the screen is trying to make it easy to understand how those 4 tools work. So you'll see them with their numbers. So number 25, matchmaking tool, and number 27 down the snake for risk assessment, and then this network model, and finally a tool called plan. Essentially what this set of 4 tools does is to prepare combinations of supply and demands that make the best possible use of reclaimed water, or combinations of different types of water, including anything you may think about. And after those combinations are set up in tool number 25, then there are two risk assessment stages. One more from a formal side in tool number 27, and then another one in the tool we're talking about today, which is essentially deployed if one or more networks are part of the equation and the analyst wants to study what risks, if any, are brought into the equation because the water is going to circulate through a network. So that is where this tool belongs, and I would like you to keep that in mind as we take a look at the software. This is a model that was prepared as a part of this setup. So I would now stop this share. Asha, can you show the software? I'll just give you a few more pointers and I'll leave it to Asha to explain the software. So this is what the software looks like. So a user of this software obviously needs a license, needs to have access to the software, so it needs to have a username and password. Once you do that, this is the home screen, and it shows you the tools that are available, and there you have them, the set of 4 tools that were developed for the project. The ones at the top, called people, network, and zones, are default environments, if you like, in the base form software. We'll probably show you something in those environments as well, but now we will concentrate on tool number 24. Just as a little bit of background before Ashik takes you through the details, what's performed by this implementation of a water quality model in a pressurized network. If any of you are familiar with hydraulic models and water quality implementations inside hydraulic models, this is you will be familiar with what we're looking at today. This is not very different from those models. It does implement the MSX library, which is a very sophisticated library designed by EPA. It was rewritten, the entire simulation engine and the MSX library. It was rewritten in Java so they could be run in this environment, which is entirely Java-based. It was designed to be part of the set of 4 tools. Otherwise, you could presumably run the same models that Rui was showing earlier on outside of this using EPANet and MSX. The advantage here is that you're inside an environment that has mapping, which MSX does not have. So it's easier to take a look at results, and you even get 3D access to georeference data. So it has a number of advantages. But I would like you guys to remember that the biggest advantage is that it's a set of, it's one of 4 tools, and that's, we wanted this to be part of this set of 4 tools for them to work together. Having said that, I'd leave it to Aisha to explain how this works, and if you're interested, obviously, in using it. Today we have limited time, but there's time for, you can ask questions today, or we can have further sessions if you have curiosity and you want to see a bit more of the models. Asha, show us how it works.
Okay, thank you. Good morning, everyone. I hope you're ready for some network model fun. So as Sergio was telling, this is the layout, so the home of the environment created for the B-WaterSmart project. Just as an introduction, on the left-hand side, you have the most recent files. So, I've been working this morning in the file to show you. Then this is the profile area I already have presented yesterday. It's very intuitive, and this is the area that takes us to administration and also to the data. Today I'll just explain this a little bit more because I think it's helpful just to so this is a typical file management environment where it's very easy to drag and drop files. So I'll just show you, for example, I'm just going to drop here the reference values from Rui. Okay, and then I'll show you an example of an MSX file. So as Sergio was telling, we have implemented fully. Oops, there's something here. Oh, okay. We have fully implemented the MSX library, and so it's within base form, and it's activated whenever we have an ENP file with. So this is the extension of a hydraulic model. And if we have an extension .msx with the same name, the software automatically assumes that we are going to use the MSX library, okay? Then I have this extra file here just to show you the composition of the file, okay? So it's, if you're familiar with the ENP files, it's a similar structure, just divided by what's more particular for the species. So you have the title, you have the options, and then and then all the species here, okay? So all of them are identified here. Some of those that Rui mentioned, ammonia, monochloramine, etc. Then we have all the constants that form the decay reaction for each of them, okay? And then how they go into the pipes and how they go into the nodes. All the formulas are clearly defined here in this file. So this was just to show you the ins of the models, okay? Then I'm going to take you to the first app. So just quick notes. It's good. Don't use the back. So the software is designed in a transactional environment where the back should not be used. Instead, when you want to go back, just click on the name on the top left. Okay, it will always take you to the back. And when you want to go to the home button, to the home screen, just click on the circle on the top left. Okay. So opening here the network model, we have two models here. Rui told me that this one is more relevant to show you. And I already had here. So when you open the model, it will come as like this, as this screen is showing. Important things. So, well, because it was already here and I already told that maps are important, you can always have a satellite view of your model or a street view or a hybrid view, okay? This is very intuitive. So if you want to go, if you want to zoom in, just click on the plus. If you want to zoom out, just click here. If you want to see a full version, click on the globe, okay? Now, on the left-hand side, you have simulation options. So you have, so in this case, Rui configured the model to run for 5 days, 120 hours. And you have the typical time steps defined here that you can change and rerun here in the simulation. The simulation log is available. So this is very, if you're familiar with AppNet, this is the typical things that we configure in AppNet, and then we see the results when doing a simulation, okay? And then we have further information. I'll just go over them, okay, very quickly. So the file information, it's on my folder, BF support, I'm the owner. Then the layers that we are seeing here. So if I wanted, for example, I could take out the junctions here. If I just wanted to see the pipes from my model or any other layer here. then this has a projection. So you can use this and have a projection and then download the shape files for this model in particular. I'll show you in a moment. Then you have all the settings. So again, these are things that you commonly define on EPANET before running a file. So the units, the flow units, and all the other options for the simulation. There we go. We have, this is the World Youth Day reclaimed water distribution system. And then you have all the exports. Okay, so in the export section here, you have several options. So you can either export the typical file .enp. Then you can also download the base form EPANET Excel, which is basically the same thing as the EPANET, but in an Excel files or in a more easy to understand way here, where you can see the junctions, the tanks, the pipes. So everything that's defined on the text file is here in tabs. So it's just more user-friendly, okay? And then you can also download the shape files. So if you click here, you download a zip file with all the shapes files that you can then transport to QGIS or ArcGIS or even Baseform. In Baseform, you can also drag and drop those. Okay, and then you have the simulation results. So this is really the thing that matters. So you can download very easily the data in Excel and then see the results and then use the results to make charts as the ones that Rui was showing. So all the results are also here. I'm just going to quickly show you. Okay, so they are all here, particularly the species. So they are here. Okay. And then last thing on this menu is that you can click on any element here, and you have the ID or the name, elevation, and other properties. Okay, for the junctions, for the links, and the tanks, and any component from your model is here. Okay, so next step is about variables and scales, because we are going to prepare us to see the relevant variables from our model. Okay, so having run the simulation, just one more thing here. One of the advantages of the Excel file is that you can, for example, edit some points. Imagine that the elevations were wrong. You could edit all of them and then import back to Baseform, and it will recognize the Excel file as well. Okay, so just keep that in mind. Going back to the variables here, as you know, in EPANET, you can define variables to check around the simulation time period for junctions and for pipes. So in this case, we're interested in looking at the free chlorine for the junctions. For the pipes, I could also define. So you have all the typical variables here, plus all the other ones that are provided by the MSX library, okay, that you could see on the visualization. For now, for the sake of simplicity, I'll just show you the free chlorine results, okay? Now, I think it's important to, I already have reverted the colors, but you can always revert the colors if you need. You can always drag here if you want to adjust the limits, okay? You can also do that in the visualization. I'll show you, but this was designed to be quite easy to manage. Okay, so here we are in the visualization tab. Okay, and the idea is really to show you the same results as Rui was showing, but within the simulation. So having the simulation going on. I will just adjust here, we can adjust the reference values. Okay, so I could go back to Rui's table, which I think I already know, but Rui, you will tell me if this is right. Rui, can you confirm? Yeah. So we can adjust the reference values here for any of the variables that we are seeing on the screen. And then, well, it's just a matter of running the simulation. So we'll start with time 0, and then we have it running here. Okay, you can always zoom in. Okay, you can always, it's easy. It's fun and easy to play with. Okay, very, very fun. And most importantly is providing us with the results for this particular variable. Okay. And so this is the way we can visualize the results. There's also another way which I can take you now. Before going to the other app, so to the network app, I just wanted to know if you have any questions. So you can write those on the chat. Okay. So here I was seeing free chlorine, but just to give you just a small hint on how, imagine that I wanted to change I just wanted to check elevation. Okay. It's as easy as that. So just clear and define a new one, and then here it's more. I always like to see the elevation because you can see the difference here. Okay, from the notes. Okay, so no questions. So I'll go to the last bit so that we can have time for questions. So the last one that we wanted to show you. So yesterday we have presented these 3 tools. Today I've just presented this one, and now there's an extra, and this is the top layer of base form. It's intended to have a very curated list of indicators to allow for a better decision making, basically. So and it's divided in 3 tabs. Today, I'll just go over the network tab, but basically it's the unit of analysis. So in this case, we are on the analysis unit of the network, of the hydraulic network, but we could be on the people or a more or another level, which is the zones level. Okay, so on this part here, what we see again on the left-hand side is a time period that we can define. And then we have all the systems. So I'm just showing this one, but we also have results for the for another model here, where the monochloramine is more useful. The maps can always change. So you have a different range of maps available. And what's relevant here is that we can see the results of the free chlorine for this model. Okay. In terms of navigation here, if you click here, you can just see the network in a different way. Today, the results of the free chlorine are here. So we are just showing results after the 3rd day. So it's the minimum values of the free chlorine from the 3rd day to the 5th day. Okay. They have the reference values provided by Rui. And if you click on any given pipe, you can see the results for each pipe. Okay, so for each one of them, let me go for this one to have a different result. Oops. I should have different results. Okay, so the idea is to have different results along the network, and we also have this because this is the end point of the network. Okay. That's this environment. Today I was also playing a little bit with, because we have some possibility of adding buildings, but this has not been tested, so I was just playing around a little bit with it. And I guess that was more or less what I wanted to show you. This is a highly specialized tool, so the part with the network model MSX is highly specialized. But then the idea is that the results can be translated in a green, yellow, red type of form, so that any person, for me, for example, I don't know anything about water quality, but I can at least understand that the results in terms of the colors that have been presented and defined here by Rui. Rui, I don't know if you want to add any specific thing about the example that may be relevant or any other.
No, Aisha, I think you did a very nice presentation of the tool. It was perfect. From my side, I don't have anything else to add. Thank you.
So we now have time for your questions, comments. Pedro Teixeira, would you like to moderate this period? We are a bit, well, not late because we were able to recover some minutes, but at least we will be having 15 minutes for this debate. Would you like to moderate it, Pedro?
Yes, of course. First of all, thank you all for your presentations, Rui, Aisha, João, and Sergio. And now the floor is open to any questions that you may have. Please feel free to ask.
So if there's no one with some questions, I may ask, is there anyone here in the session who models the networks? I mean, is somehow familiar with the EPANET? No. So the point of my question was to see whether it was easy for those who are used to this kind of environments. How do they see the advances that were included? And at least from my side, I'm the exact opposite of Aisha. I know about water quality and the mechanisms behind it, but really, I'm a chemical engineer, so my expertise is not the hydraulic modeling. So we are very complementary. And the thing for me is that, as Aisha has shown, the results, the outputs of the model are quite easy to understand, user-friendly, and the manager really has a way to use it and to act according to what is clearly seen. And having said that, I think it's important that because this is it has something or a lot of things behind the equations. This tool was particularly designed for planning, for support the planning. I mean, as the key tool to manage the risk of water use in terms of the distribution, so to prevent the regrowth, as we have all been saying. But it can, depending on the expertise and the team that the water utility has, who manages this system has, it can also be used for supporting the operation. But well, since we don't have there's no one trying to using it, so perhaps it can be more difficult to assess this feature. The other thing that perhaps we can highlight is the importance when we go into to the supply to distribute reclaimed water is a key water quality parameter is the ammonium, which I'm not sure if I can say very often, but at least there are many times it is underlooked, and it impacts a lot on the disinfection barrier that the same dosage of free chlorine represents. And I think it was an output very clear from this presentation. Oh, thank you, Brace. Thank you for your comment on the chat. While you're thinking of more questions, I would like to invite you to fill in the evaluation form. This is a training session, so we should, it's on the chat.
Yeah, it's on the chat.
And before I forget, I will be very pleased to invite you to join our last training session next month on the 23rd of April regarding the direct potable reuse, a solution that has been developed by Águas do Tejo Atlântico, also a partner of the Lisbon Living Lab within B-WaterSmart and with our support, LNEC support. So it will be next 23rd of April, and we will be most happy to have you here with us again.
Can I say something?
Sure.
I just want to give you congratulations because it was a really nice presentation. I think that even for non-chemist people, your presentation was very clear, and I liked very much to see the results on the base form application. It's really nice to see those colors changing. We know theoretically that occurs, but to see that visually is really quite nice. So congratulations for the team.
Thank you.
Yes, it's at the same time. Next April session will be also from 10 to...
No, I think it's 10:30. 10:30 CET.
Oh, sorry.
I think so. But we have the Viz, which is here, that can...
To be honest, I guess Maria do Céu Almeida change it to 11 a.m.
Yeah.
Not, I guess. He's saying
11 Lisbon time or
No, 10 a.m. Lisbon.
CET?
Yeah.
Set, okay.
Set is 11, I guess. 11, yeah, I guess. I was trying to find the email to be...
But yeah, we may send a reminder of these closer to the event. We will send a reminder, and you will all be able to have a look at to confirm the link and the time.
The time, yeah. I can add that we can change the time at the Nextcloud platform as well. When we have that final hours, I will put it on Nextcloud calendar to be easier for everyone.
So if there's no one left and there are no more questions or comments, thank you all for your attention and precious time. It was again our pleasure to share with you the work we have been developing, some part of the work we have been developing for the last 3.5 years. And for those of the Lisbon municipality and other colleagues which will be going now into the hands-on training session, see you in some minutes, and the other ones, see you in April, and all the best. Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Bye-bye, everyone.
Este número dos microfones, a gente tem que comprar uma porcaria de uma coisa. É tudo